Greetings, my people. I hope we're doing well today. This is the second video that I'm posting for Product and Quotient Rule, but since this is the first one that is kind of necessary, I'm still calling it Product and Quotient Rule Part 1. The other video was how we basically derive the formulas, so sort of a proof of the formulas that you see in front of you right now. Product and quotient rules are important. In the last section we saw sum and difference formulas. Well, it wasn't really a formula per se. I mean, sum and difference functions are really not all that complicated, and therefore we just need to be assured, which should be our assumption, that we can go ahead and do them term by term, and that is indeed the case. When we get into product and quotient rules, however, those are sort of a different order, and therefore we have to have different formulas, and for those of you that wanted to see it, I wanted to go ahead and derive those or prove those formulas for you. I hope that was enriching and helpful and all sorts of fun stuff like that. For those of you that skipped over that video, these are the formulas for product and quotient rule. They should look familiar because they're the ones that we dealt with last year at the end of the year when I was getting a couple sections into calculus before sending you home for the summer. You need to see the fact that the product rule, that first one, it's really easy. You just need to remember that if you have two factors, one of the factors has a derivative taken in one term and the other one has a derivative taken in the other term. It's really easy because multiplication in each of the terms and the sum, the plus sign which actually connects the two terms, both multiplication and addition are commutative, so you can actually get the order mixed up from here, and it actually still is the same thing. What we have here when we have the quotient rule, we unfortunately have to remember the order, and you just have to remember that the bottom comes first. So the numerator looks eerily like the product rule. It's just the fact that we have to remember which one comes first because it's not a plus sign, it's a minus sign, and subtraction, of course, cannot be done in any order. And then you just need to remember that the bottom is squared to round out the formula. Now, the quotient rule is one that people don't particularly care for. Okay, I had a student a couple years ago, his name was David, loved to try to get around the quotient rule. And if you remember from last year, I even discussed that with y'all because if you're given a quotient, you can always represent the denominator as raised to the -1 power and turn it into a product and use what's called the chain rule. That's good and clever, and my student David, he did that every single time. He refused to use the quotient rule. The problem is that there will be a few, not many, maybe one or at most two questions on the AP exam that might ask you a question that requires you to know the quotient rule. And if that's the case, you're going to need to know it. On top of the fact that once you get in and start using it, it becomes second nature, just like the product rule does, and it really doesn't wind up being that big of a deal. So, without further ado, let's go ahead and jump on in. Now, back in a previous lecture, and I'm going to give you an even easier version of it, we had a product function, something like that one, right? And what we did is we went ahead and multiplied it out, and we wound up doing it term by term. What I want to do at this point is show you that if you are actually to use the product function, it actually winds up, the product rule, it actually winds up being the same derivative, which we should assume, but it's always nice to actually see that and have it shown to you, okay? So if I take the derivative, I know that it's the first times the derivative of the second. Now remember, I told you last year, I use these brackets not because it's official notation and not because it's required, but it's sort of a visual cue to me which factor in this particular term is the derivative of one of the ones above, right? So actually I did it in reverse order here, so sorry about that. I'll go ahead and put the 2 right there. So it's the first times the derivative of the second. So this is actually the derivative of x plus 1. And then we have the derivative of the first times the second. So, I can color code these if that makes it helpful in terms of being able to see it. The x plus 2 gives us those two. okay? And the x plus 1 gives us those two, okay? The x plus 2 stays the same here and has the derivative taken of it over here. So in terms of our formula up here, the x plus 2 is my f. So here's my f, here's my f prime. This is my g right here. So here's my g prime, and here's my g. And so that matches up perfectly with what's above. And so I just have x plus 2 plus x plus 1, because both of those binomials get multiplied by 1. And therefore I have 2x plus 3. Now, if you were to differentiate this term by term, what would you get? Well, of course, you would get 2x plus 3, okay? Now, there are ones that are absolutely, it's just absolutely asinine to try and do them by the product rule. This is one of them. There are ones that are sort of in the middle ground somewhere. So let's say I'm given h of x, and I'm given 3x minus 2x squared and 5 plus 4x. Now that's still a binomial times a binomial, but sometimes when it's not, a linear times a linear, some people kind of go, oh gosh, sometimes I screw that up. And of course, this one is in reverse order. It's not in descending order. It's in ascending order, and sometimes that messes people up as well. And so you could actually go ahead and do this one by the product rule. So we'll go ahead and leave the first one alone. Take the derivative of the second. Take the derivative of the second one, or first one, and leave the second one alone. Now, that winds up not being, wonderfully helpful, because you still have a little bit of multiplication to do. But you do understand that this one is simply not as easy as this one, and therefore there would be some people who would prefer to go ahead and do it by the product rule, and if you're one of those people, then please, by all means, go ahead and do it. There are, however, ones that cannot be done except by using the product rule. And if you have something like that, where the two functions, especially this one, because these are of two different classes, right? X is from the polynomial family, sine is from the trig family, and so you can't really get the derivative of this with what you know right now unless you use the product rule. And we haven't officially gotten to trig, but you should know from the couple of examples from previous lectures that the derivative of sine is cosine. So we'll take the first times the derivative of the second times the derivative of the first times the second, and we wind up with x cosine x plus sine x, and that winds up being the derivative of that particular product function. For those of you who are on the Skype session on Saturday, I'm sorry, I'm going to try and do as many as possible that are different from the ones that we covered on the Skype session, but ones like this I kind of have to do in order to make that particular point that I just made. So it's not going to be a complete rehashing of what we did on the Skype session, so please don't tune me out just yet. Now, so that basically is a couple of examples, and we can do another one, and we know like e to the x times sine x instead of x sine x. It's not hugely different, but I know that p prime of x, I know that's the first times the derivative of the second plus the derivative of the first, and of course the derivative of e to the x is e to the x, and like I said, I promise to explain that to you in future videos, but you actually don't know enough right now for me to actually demonstrate to you that that is indeed the case. You're just going to have to believe me. And you don't have to clean it up by factoring out the e to the x. You can. It doesn't really matter. So what we're going to do from here is we're going to do a couple of examples of the quotient rule. Okay? Let me go ahead and see if I can find a good one. How about f of x is equal to x plus 1 over root x. That's a fairly simple one. It should be relatively easy. Let's go ahead and do it by the quotient rule. And we have the bottom times the derivative of the top, right? Because remember that if we're taking the derivative of, and this I won't do f and g, I'll just do u and v since it cuts down. You have the bottom times the derivative of the top times the derivative of the bottom over the bottom squared. So instead of f and g, we just have u and v. It's the same deal. So you have v times u prime minus u times v prime. And of course, to take the derivative of root x, you must conceive of it as x to the 1/2. So you have 1/2 x to the negative 1/2. Put it in brackets to remind myself that that's a derivative of one of the factors. And then of course the square root of the square root of x is just x. Now, if we need to go ahead and simplify this, which actually we do because that negative exponent right there implies a complex fraction, we'll multiply through by root x over root x, and we're going to go ahead and get x minus 1/2 times x plus 1. Actually, let's go ahead and multiply by 2, and that gets rid of the 1/2 right there. And we have 2x to the 3/2, or we have x minus 1 over 2x to the 3/2. Now, did I have to do this one by the quotient rule? And the answer is no, because remember, monomial denominator right here. I could have actually changed that into x to the 1/2 plus x to the negative 1/2, okay? And then done 1/2 x to the negative 1/2 minus 1/2 x to the negative 3/2, which of course, if you have 1 over 2 root x minus 1 over 2x root x, in order to get a common denominator, I'm going to have to multiply this one by x over x, and I'm going to get x minus 1 over 2x root x. And if you know the relationship between radicals and fractional exponents, you'll recognize the fact that that is identical to that. Okay, so even if you didn't do your necessary, or not necessary, but your advantageous stop, think, then do, you still are capable of getting to the right answer, because this done by the quotient rule is identical to this simplification after having broken it up and simplified and done it by the power rule. Okay? Now, let's just say that I wanted to get now remember, this is the derivative right here. This is f prime of x, and the original was f of x, x plus 1 over root x, okay? And let's just suppose that I was asked for the equation of the tangent line at 1/1/2, okay? Now, what I need to do at this point, since I already have the point, knowing full well that the two things that I need in order to actually no, this is the wrong one. But let's go ahead and do it. That's not 1/1/2. It's 1, 2. Okay, because when you plug in, you get 2 in the numerator and 1 in the denominator. But same principle holds. I just had to change the order pair real quick. So I have the point at which I'm going to find the tangent line. Now all I need is the slope, which means I need to evaluate that at 1. And when I evaluate it at 1, a strange thing happens. It actually winds up being 0. So you actually have a horizontal tangent line for that particular function right there. And so y is equal to 2 is your tangent line. Okay? Sorry. That ordered pair is actually for, the ordered pair that I originally put up there is actually for finding the equation of the tangent line of the reciprocal of that particular function, which I planned on doing. So let's go ahead and do that now, okay? Now this one, you cannot change the, well, I mean, you can change the form. It's just not advantageous to try and do it to get around the quotient rule. You're going to have to do the quotient rule. You have a binomial denominator. So monomial denominator, you can change the form by separating the fractions and simplifying, okay? Binomial denominator, you're stuck, man, okay? You're just stuck. So I know that g prime right here, going to go bottom times the derivative of the top. And some of these derivatives you're just going to start to memorize. You're going to see them all the time. You're just going to start to see root x and just know right off the bat that it's 1/2 x to the negative 1/2. The derivative of the bottom times the top, and we'll go ahead and write it as a fractional exponent as well, just so it's sort of a continuity of representation. And then it's x plus 1 squared. Now, just like the last one, you have a negative exponent in the numerator, which implies a complex fraction. So it's always a good idea to get rid of that. I also want to multiply through by 2 in order to get rid of that. So when I multiply through by 2 root x, in the first one, it's going to completely cancel out with that and leave me an x plus 1. When I multiply in here, it's going to turn this one into 2x. And this, in the denominator, is going to be 2 root x, x plus 1, or negative x plus 1 over 2 root x, x plus 1. Now, that is the derivative of the original function, okay? Now, I have a point. What I need now is I need the derivative at that point. So I need to evaluate g prime of 1. Well, a strange thing happens. You get 0 when you plug it into that numerator right there, okay? And therefore, this one, you happen to have a tangent line of y is equal to 1/2. Let's go ahead and do one more example in terms of the quotient rule, and then I'll sort of pause and I'll start the next video so that none of the videos are too long. And this one will actually be a little bit more straightforward, no radicals. Let's just go ahead and try to get the equation of the tangent line of that function right there at the ordered pair 2, 3. Well, the first things first, I'm going to have to go ahead and I'm going to have to do the quotient rule in order to find it. Now, could I change the form of this one? I could. I mean, you know, if I actually do the division, you actually wind up with that, okay? Until you know, I mean, it's a little bit advantageous, I suppose. I mean, it's not hugely so until you know the chain rule. Because, well, yes and no. But we'll get into that. Let's just go ahead and do it by the quotient rule, since that's kind of the point of this whole section. We have the bottom times the derivative of the top minus the top times the derivative of the bottom, all of that over the bottom squared. Okay? Now, when you distribute this x, you're going to wind up getting negative 2 over x minus 1 squared. Okay. Now, if you watch the video on the proofs, you know the reciprocal rule, so you can kind of see how this is the derivative of that right there, because of course the derivative of that term 1 is 0. Now, I have this function, and in order to find the tangent line, I need to evaluate this derivative function at that x value, right? Because this derivative function describes the slope of this original function at all x values, including the x value of 2. So I wind up with negative 2. So I have point slope, and I know that y minus y1 times m times x minus x1, it is really as easy as that. Okay? The point at which the line is tangent to the curve is your x1, y1, and the slope at that point is the slope of the line. Okay? I'm going to go ahead and stop the video here. We're going to go ahead and have another one with another batch of examples and stuff like that. But I hope this is helpful. If it's not, or if there's any sort of unanswered questions, go ahead and leave me a comment or shoot me an email. But if you're raring to go ahead and queue up video 3 and shoot me any emails after that one. Bye.